structure that are statically indeterminate. What does that term actually means? Okay, I think that's important. So if we have a structure now, okay, we have a bar. The bar is supported at both ends. Okay, the bar is supported at both ends. And I would like to call this point A, point B, point C, and point D. Okay, and at each point B and point C, we have a force in this direction, and this is 500 Newton, and this is 200 Newton. Okay, and then we have our transformation where this is X and Y, and this is the rotation in our Z. Okay, so we are going to construct our free body diagram. Right, we're going to construct a free body diagram, and to construct a free body diagram, okay, we are going to again over here, this is equal to 500 Newton, and over here is our 200 Newton. Okay. The frustrating thing is this. Okay, hold on. The frustrating thing is this. Okay, so this is our point A, our point B, our point C, our point D. The frustrating thing is this. Okay, what is the reaction force at point A and point D? Okay, when I was young, less experienced, okay, I'm always frustrated. Point A and point D, are they pointing inwards or are they pointing outwards? And it has to be a logic why it should be one way and not the other. Okay, so what do I mean by is it pointing outwards? So is the force at point D pointing outwards, or is it pointing inwards? Over the other side, is it pointing outwards from A, or is it pointing inwards? Okay, so that is the frustrating question, right? Because I don't know about you, but for me, if I don't get the correct assumption of the reaction forces, I always have doubt. Okay, so once this is the very beginning of the analysis. If at the very beginning of the analysis you get frustrated, okay, you have not a clue whether what you are solving is right or wrong. That is common for this problem. So can anyone tell me, is it assuming going outwards or inwards, and why? Anyone, please?
Outwards, because it's
Yes.
tension.
Your answer is right. Outwards is correct, but it's not necessarily equal to tension. Okay, so the answer is right. So this is not a good assumption. Okay, so what I've put down, that is a good assumption. So this is your dy, and this is your ay. The next thing is y, right? I don't want you to come with, okay, because he has more experience, you know why. I have less experience, I don't know why. Fine. No. Okay, why? Okay, I can explain to you in a simple term that you can relate. Okay, now those of you who are staying in Oakville, the houses are very close to one another. Okay, so this is house number 1. This is house number 2. Okay, so if you were to ask me what view am I looking at, so this is the door for house number 1, and this is the door for house number 2. Okay, so it can be a garage door or whatever door or entrance door. So So if you were a human being, what you will be doing is you are standing this way. So you are very tall. Okay. Okay, you're very tall with your arms. Now, if you want to go upwards, your hand has to push which direction? Outwards or inwards? Anyone? If you want to climb up, huh?
Outwards.
Yeah. So your hand, your strength, okay, your force, your hand has to push what? Outwards, so that you will not fall. Yes or no? Right? Likewise for this, the beam is stationary over there. Okay, it's not falling down. For that to happen, it is a logical, okay, it's a logical assumption that we make to prevent it from falling down. We don't have y forces, we only have x, dy and ay have to be pushing upwards. Make sense? Okay, that is a good assumption. Okay, if it was to push inwards, right, or the one I've cancelled, means the bar will be dropping. Okay, so I want you all to use logic like this. Okay, not memorizing, because if you're going to memorize, the next course you take, you're going to forget everything. Okay, so once you have that, you are going to write down, we're going to assume, okay, we're going to assume ax. Oh, sorry, this is x, not y. I do apologize. Okay, when that's done, we're going to assume ax and dx are pushing away from member AD. Okay. Then we go into static analysis. Okay. Now, just to recap, what I'm trying to prove down here is I'm trying to prove that this structure is statically indeterminate. Means you cannot just use static analysis to solve the problem. Okay, that is our objective. So, okay, let's do something simple. Okay, so static analysis means we are going to take moment about point Z, about Z axis at point A is equal to 0, right? And you cannot form any equation, right? Because moment is equal to force multiplied by perpendicular distance. Okay. All our forces have no perpendicular distance at all, right? So perpendicular distance, so this is the distance we are interested in to take moment about the z-axis, right? And all this distance are parallel to the what? To the applied force. So there's no moment at all for that reason. Okay. Then next we are going to take that summation about forces in the y direction is equal to what? 0, right? So any y, so we are following this transformation. You also have no y forces. Okay, but we do have x. Okay, so the right hand side going towards the right, summation of forces in the x is equal to 0. So you will have minus ax plus by 500 plus by 200 plus by dx. Okay, so you just tidy things up. Minus ax plus dx is equal to minus 700. So the problem is this. Okay, now you only have what? So what we have just done, we have just completed our static analysis.
Dr. Eugene, sorry to cut you off. You said the reason we don't have momentum is because
Moment, not momentum.
oh, sorry,
Moment.
moment. Sorry. Is because we have two parallel forces. We don't have anything going up or down, right?
Yeah, we don't have it going anything. So what I highlight over here is this distance over here. Why I draw this is this distance are all parallel to the applied force. Okay, does that make sense to you?
Yeah, okay.
Yeah, it's not acting perpendicular. That's why it's not a moment at all. Okay. So from here, right after so we have completed our static analysis only. Okay. So what we have done is we only form one equation. Okay, we only form one equation with two unknowns. So we know mathematically we cannot solve this, right? So after the static analysis, okay. Right? So we complete our static analysis. We should have done is we have summation of moment, we have summation of forces in the y, summation of forces in the x. Okay, we cannot solve it. Okay, because one equation, two unknowns, we cannot solve it. So this is where we call this is where the structure is identified as statically indeterminate. Okay, we cannot use static analysis to solve it. So what we can do, okay, to solve a problem like this, okay, to solve a problem like this, we must employ, okay, elastic deformation. Okay, we must employ elastic deformation to solve the problem. So remember last week when I started the class, I mentioned what? We are going to combine both static analysis and elastic deformation to solve for structures. Okay, and this method of solving structure reaction forces can help or can solve a lot of any complex loading. Okay, so it's like the ultimate analysis that you need to know. Okay, questions so far? Anyone? Okay, so I don't hear anything. So what I'm going to do now, okay, we are going to I'm going to look into the solution procedure. Okay, so just bear with me. We're going to look into a solution procedure. Okay, I'll write down the solution procedure for you. So the solution procedure. Okay, to analyze statically indeterminate structure. Okay. So the key thing is we have to include or redundant reaction. Let me write this out first, okay? Then when I later on mention what do we mean by redundant reaction, okay, then you understand where this is going. Okay, so let me write the theory out first. So redundant means not necessary. Okay, so redundant reactions are placed with unknown loads, right, which along with other loads or other applied loads